Hi, my name is Dr. Mark Abelins. This is another in a series of short informal tectonics videos intended solely for use in my fall 2014 sections 7 and 8. This particular video is about hot spots and the driving forces behind plate motion, those two topics. First, hot spots. What is a hot spot? Where are some hot spots located? A hot spot is a place where there is volcanic activity within a plate. So here, for example, is the Pacific Plate. There is a hot spot located on the Pacific Plate, coincident with the big island of Hawaii, which is located right about here to the southeast of Honolulu. Big island of Hawaii, that's a hot spot. It's a place where there's volcanic activity within a plate, not near the edge of the plate, not near a plate boundary, but within the plate. Big island of Hawaii, a hot spot. Another place where there's a hot spot is Yellowstone in the western United States. Now, Yellowstone is right about here, where I'm moving the cursor right now. May not be as obvious as with the big island of Hawaii that Yellowstone is within a plate, but it is. Yes, there is a plate boundary to the west of Yellowstone, but it's many hundreds of miles to the west of Yellowstone. And the volcanic activity associated with that plate boundary is far to the west, the Cascade Range out in Oregon, Washington State. In contrast, Yellowstone is several hundred miles to the east, is a different thing. Another one of these hot spots, a place where there's volcanic activity within a plate. Now, the hot spot, let's use Hawaii as an example. The hot spot is above a mantle plume. And a mantle plume, that's warm, less dense rock rising within the mantle. Bear with me for just a moment while I locate an illustration. This is the one that I seek. Big Island, Hawaii, hot spot. It's above a mantle plume. Warm, less dense mantle rock that rises. It's rising beneath the hot spot, which in this case is located at the Big Island of Hawaii. And as the warm, less dense mantle rock gets closer to the surface, a little bit of it melts, like 2-3%, and then that melt rises up, ultimately solidifying underground or spilling out on the surface as lava. Well, that explains the volcanoes of the Big Island of Hawaii, but what about these other islands? Well, let's look at these other islands. You can see that they get older the farther to the northwest you go. Hawaii, volcanic activity today, quite possibly literally today. Tune into the USGS Volcano Observatory on the Big Island. Tune into that on the web, and you may see volcanic activity that's happening today. It's about 700,000 years to present, to right now, the Big Island of Hawaii. It's still growing. But Maui, it's a little bit older. And then Molokai, 1.3 to 1.8 million years old. Oahu, 2.2 to 3.3. Kauai, 3.8 to 5.6. And the islands just keep getting older. Like way off to the northwest is Midway Island. It's 27 million years old. So they're getting older and older as you go to the northwest. Also, only the Big Island of Hawaii has active volcanoes on it. The other islands had volcanoes on them at one time, active volcanoes on them at one time. Now they only have extinct volcanoes, eroded volcanic mountains. The only active volcanoes are on the Big Island. Well, so why? Why does it work this way? Well, what it is that the islands are moving along with the Pacific plate, while the mantle plume, the warm, less dense rock that is rising in the mantle, is more or less stationary. So the plate's moving, the plume stationary, and over time, the island that is at the hot spot, the island that is above the plume, is carried away atop the plate. In case you need a refresher, the Pacific plate is moving off to the northwest. So these islands are being carried off to the northwest as time passes. They're being carried off by the moving plate. Hot spot, active volcanoes above the mantle plume, these other extinct volcanoes off to the northwest. Islands have been carried off to the northwest. Here's an animation that shows how this works. I think is pretty nifty. Here comes the rising, warm, less dense mantle rock. A little bit of it melts. The melt rises, and it feeds volcanic activity at the hot spot. And then over time, that volcano that grew at the hot spot is carried away from the plume. The volcanoes go extinct. No longer any active volcanoes on that old island that's been carried away. A new island grows at the hot spot above the plume. And over time, you get a whole chain of hotspot volcanic islands, as shown here. Now, remember, here it's labeled chain of hotspot volcanic islands. The hotspot is here, where you have the active volcanoes, where you are sitting atop the mantle plume. Regardless of the way this is labeled, yes, they're all part of this chain. They all formed at a hotspot. Just be clear. Just remember, the hotspot, that's just right here. And then the second topic, driving forces. Why are continents moving? They're kind of big and bulky. As I mentioned at the very beginning of all this, if we all get out and push, we're not going to be able to move one. Now, there is some bad information circulating on the internet. There are people out there who don't know much about the Earth and much about how all this works, who think that as the human population has grown, just the weight of all the additional people has started to shift the continents around. If we all get out and push, or even if we all just stand around, all the people who are here on Earth now, there are so many more of us than there were just a few years ago, we're not going to be able to move continents. But what does? I mean, they're big, they're bulky. What can actually move North America, or Africa, or South America? What can move any of these? And ultimately, it's about heat transport. The interior of the Earth is hot. The exterior of the Earth and space are cold. Heat is moving from the inside to the outside. Within the mantle, transport involves convection. And there are some nice animations of this. Let me show you one of these animations that came from the publisher. And what happens is that warm, less dense parts of the mantle rise, cooler, denser parts of the mantle sink. And that transports heat from the bottom of the mantle to the top of the mantle. Heat transport, mantle convection, they're sort of ultimately behind plate motion. But there's more to it. And some of the more to it is right there. Let me go back so you can see it again. Slab pull. Cold, dense oceanic lithosphere going down at subduction zones that pulls a plate along. Slab pull. Also, the mantle rock just flowing along the base of the lithosphere. rock in the asthenosphere flowing along the base of the lithosphere, traction at the base of the lithosphere, like right here, that influences the way the plates move. And finally, an important part of all this, there's the slab pull, there's the traction at the base of the lithosphere. It's here at the ridge, what is called ridge push. Gravity pushing down on the mid-ocean ridge, on the elevated seafloor there at the mid-ocean ridge, gravity pushing down on that forces the plates apart. So you've got three, ultimately it's heat transport, ultimately it's convection in the mantle that drive plate motion, but in detail, there are three forces behind plate motion: slab pull, traction on the base of the lithosphere, and ridge push. Wegener didn't know about those. Nobody knew about those back at the beginning of the 20th century. He had some ideas about what might move continents. His ideas were wrong. Others in his day, other scientists in his day were able to show that his ideas were wrong. Today, scientists know a lot more about the planet's interior. A lot more was learned over the course of the 20th century. And now, given what is known, these plausible mechanisms for plate motion are understood to exist.